Hey everyone, welcome back to the channel and welcome to the very first video in our playlist dedicated to learning containers and Kubernetes. Now before we jump into what containers are and how do they really work, it is really important to understand why we even need containers at the first place. So here is how I see it. If we want to understand why containerized applications became so common, we need to understand and look at two main reasons.
First, the evolution of virtualization technologies, which is basically the shift from running everything on the physical server to using virtual machines, and the growing need for better isolation for the apps running on those virtual machines. Second, the evolution of application architectures from monolithic architecture to distributed systems. This shift from monolithic applications to microservices required a new way to package, ship, and run the software.
Now if that sounds interesting and has already caught your attention, then watch the video till end and I will walk you through the journey of understanding why containers.
Wherever you work, you have probably noticed that software applications are huge assets for any organization. In fact, businesses and their applications are two sides of the same coin. And while this applies to pretty much every sector, I want to take aggregator business model as an example. These companies don't own any physical assets. Their main assets are their applications. Uber doesn't own fleet of taxis in every city. Airbnb doesn't own hotels unlike Hilton and Marriott. Yet all these companies run a massive business. And what they really own is their software applications. And given the scale at which these businesses operate, they must run their applications in a robust manner to keep things going. So the next question is, how do they do it?
To understand that, let's go back in time and imagine the world before containers, even before virtualization.
At that time, we used to run applications directly on physical servers where multiple applications would share the same machine. But there is a problem with that setup. Without isolation, if one process starts consuming most of the resources, for example CPU and memory, then the other applications on that server shows performance degradation. So the problem was that there was no proper way to define resource boundaries on a single physical server, and that used to lead to a lot of resource allocation issues. If one application had a memory leak or high CPU usage, everybody else on that box suffered. So there was need for obvious isolation. Now you might say, let's just run each application on its own physical server. That sounds like a great solution, right? But this solution doesn't scale either. We ended up underutilizing resources on the physical host was one of the problem, and it became expensive to maintain so many physical servers. And the problem doesn't end here. If the business had to scale and we need to build a new application to support, then we had to procure a new server each time, and that process generally takes time. This could take weeks or months of waiting for hardware delivery and setup. I am pretty much sure every one of you would have experienced this.
Alright, that's a lot of pain points, right? You can understand that we needed a better solution for running our applications. And that's where the virtualization came in. And honestly, it changed everything.
The introduction of virtualization and virtual machines changed the game. Using a virtualization technology called hypervisor, we could basically split one physical server into multiple virtual machines. So instead of dedicating one whole physical machine to one app, now we can run several apps, each in its own VM and on a single server. Now we only buy a new server when there is no room left to launch another virtual machine on that underlying physical host. For everyone's quick understanding, I wanted to share that the hypervisor, such as VMware ESXi, is a lightweight OS that runs on the physical hardware to enable the virtualization, and that allows multiple VMs to run on it simultaneously. And obviously, this provides better utilization of the physical server resources. Each VM acts like a full server. It has virtualized hardware, virtualized CPU, virtualized memory, virtualized storage, network, and you can install a full guest operating system inside it, such as Windows or Linux. Each VM can run a different application completely isolated from the others. But one thing that we needed to understand here is that though each VM provides full isolation, this also carries the baggage of a full operating system. That means if you run 3 virtual machines on a host, you have 3 separate OS instances, all running on the same underlying hardware. And that brings new problem to the table. First, each VM requires its own OS, and hence we need to budget for additional OS license cost. Second, each virtual machine has its own operating system footprint, because running multiple full OS instances uses a lot of CPU, memory and storage. And third, which we cannot ignore, is that each virtual machine needs regular security patching and hardening that is required for every single VM, and this increases the administrative effort for the ops team. So while virtualization improved things, we started asking ourselves some real questions like, can we cut down on OS license cost? I mean, why pay for a full OS on every single VM? Can we shrink that OS footprint, that additional CPU, memory, storage required for each VM? How to save time and effort on all the patching and maintenance that comes with managing so many VMs? Because you see, we were provisioning VM for each app. Then are we getting better utilization of the existing physical service resources? Can we bring down our hardware cost by using fewer physical machines and squeezing more out of the existing ones? And how do we make infrastructure provisioning faster, especially when teams are waiting to deploy apps? But to deploy apps, they need to procure the server and the VM. At the same time, the need for isolation between applications was always the requirement. And the answer to this question was containers. Containers help to answer all these problems that we just discussed. Let's go back to our physical server. And now instead of installing a hypervisor and creating virtual machines on that physical host, with each one having its own OS, now let's install just one OS on that server. After that, we install a container runtime such as Docker Engine or Containerd or Cryo on that OS. In some sense, this runtime is similar to the hypervisor in VMs, but this runtime operates at the OS level rather than the hardware level. And this container runtime helps to run the containers on the machine. Each container provides an isolated environment for the apps, but under the hood, all containers share the same host machine's OS kernel. Inside each container, we can bundle our application and all its dependencies and libraries and runtimes like Python, Java, and config files that app needs to run. So basically, by using all these dependencies, by bundling all these dependencies and runtimes and binaries, we package it into an image, which then container runtime helps to run as containers. Don't worry if you don't know the container runtime or image, because that obviously we are going to discuss later. But that's the idea I just wanted you to give here, that what we do with containers and how we run those containers. Okay, so now we know that the container is an isolated environment where all the apps, dependencies, config files, binaries, libraries, all are bundled together. And then we run the container on the machine, and container runtime helps to run that container, fully isolated from the other containers on that host. Also, as there is only one OS kernel to maintain on the host, so we eliminated the additional overhead of maintaining multiple virtual machines. Now there is no need for extra OS license as well, so we saved on the cost also. Now there is actually another container deployment architecture that is pretty common across organizations. Instead of running containers directly on physical servers, we first use virtualization to create VMs. Then install container runtime inside those VMs, and then finally run containers within them, each as an isolated process. So what we are doing here is combining best of both worlds, virtualization and containers. We still get the full isolation that VMs provide, but now we can also run multiple apps inside a single VM using containers. something that was not really safe to do before without risking the conflict between the apps. Containers help isolate the apps from each other inside the VM, and the VM itself isolate the containers and everything from the underlying infrastructure. And important to note here is that since containers let us run more than one app per VM, we don't need to spin as many VMs as before, because earlier we were doing one app per VM, right? Which is no more a limitation. This brings us to the end of the first section, where we discussed how the evolution of virtualization helped us weave the container story.
So while virtualization was changing how we use servers and compute, the way we design applications was evolving as well. The evolution of application architecture and the shift from monolithic to distributed systems like microservices and event-driven systems naturally pushed us towards container. Before I proceed, I must say that here we are not discussing monolithic and microservices architecture differences, as that itself can be a separate topic. Here I'll stick to the main points with respect to application architecture that helped us move towards container.
Coming back to the point, traditionally applications were built as monoliths, one big unified codebase, and had their own set of challenges. With every new feature added to monoliths, compile and build times kept increasing further. Making changes gets slower because you have to consider the impact on the whole system. Changing one functionality or the feature can break the entire application, so we had to be more cautious, and it led to slower development. We can't scale individual parts of a monolith. Scaling the entire application requires deploying new instances, which is inefficient and expensive at the same time. Upgrades, patches, or migrations, even for a single function within monolith app, required full downtime, disrupting all services for clients, which is definitely inefficient. And running monolith requires expensive and high capacity hardware such as compute, memory, storage, networking to run the entire application. So we started thinking, is there a better way to design applications so we can avoid these problems? Let's run the components separately. Why not? Let's scale the pieces individually, and not all components need to be scaled together. We wanted to deploy components individually and wanted to iterate faster on the features. That's how we moved to microservices. Each microservice is carved out of the original monolith, separate from one another, but when grouped together they recreate the full app's functionality like original monolithic application. This push to distributed architecture brought cost savings, as microservices can be deployed on separate servers with only the necessary resources. Unlike monoliths, they don't have to be provisioned with expensive and high capacity hardware. Individual scaling is possible for each service due to its modular architecture, and we can scale without carrying the baggage of the entire application. Microservices enables faster feature release due to independent development cycle, and developers were able to iterate faster. No need to recompile or restart an entire application, unlike monoliths, and as no full service disruption during upgrades, updates are rolled out one services at a time. However, running applications in a distributed way comes with its own challenges, and it's not easy. The next challenge is where to run these microservices applications and how. Definitely you would have come across this term in the cloud native world, that is dependency hell. I'll tell you what it is. So suppose if we decide to deploy multiple applications on a single VM, there may be a possibility that different libraries and runtime requirements may conflict with one another, as different apps may need different libraries or runtimes. One of the running app depends on a specific version of a library that conflicts with the version another app B needs. If we try to run services on the same VM, these dependencies can clash and can bring down the both applications. So just let's take a step back and think what you were required to do in the past when you had to run any app or set up a platform. Let me give you a real example. I was recently working to set up the Confluent Kafka platform. Just take a look at the system requirement for deploying Confluent Kafka. First off, the application had to be compatible with the underlying OS, Linux, Windows, AIX, whatever. Then came kernel version dependencies within the OS. If you have already decided on OS and kernel version, then came the Java version compatibility between applications. And don't forget all the other library dependencies. Basically, to run the app, we had to check OS compatibility, kernel compatibility, library compatibility, and even during the product upgrades and patches, we have to take care of this compatibility once again. So after discussing about the problems for a while, we understand that there was a need for encapsulation of cross dependencies between the apps. There was a high need for isolation between the applications, and there was a need to eliminate the environment drift across dev, staging, and production. As the library version and other dependencies version might be different across different environment. So the elimination of drift between the environments is a definite yes. With containers, we are able to run each app in an isolated way, which includes its own environment with their own libraries and runtimes such as Python, Java, along with other configs and binaries. This helps prevent the clashes between the apps that depend on the shared libraries or runtime versions. Isolation between apps ensured one app can't accidentally mess with another's data or runtime state. And most importantly, since the whole environment is packaged into the container, there is no environment drift. What works in dev will work exactly the same way in staging and production. Containers help replicate the exact environment with all dependencies, libraries, runtimes bundled together. Okay, that was a long video, but as I said, without knowing the why behind containers, it is really difficult to appreciate the benefits that containers bring to the table. It's time to end this video, and for the next video you can subscribe to this channel. Thank you for today. Thank you so much.